Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. In this module today, we are going to talk about the elastic scattering and the scattering cross-sections from the paper Classical Mechanics. After studying this module, you should be able to understand the kinematics involved in elastic collision between two particles in the center of mass frame and in the laboratory frame, which we will define. You will learn about the scattering of a particle once the particle interactions are specified in terms of the force field, and then you will be able to calculate the scattering cross sections once the force is specified. Why is it important? See, the analysis of data obtained through scattering of particles on fixed or moving targets, this has emerged as one of the most powerful tools used by particle physicists to unravel the nature of fundamental interactions and the existence of hitherto unknown particles. Large Hadron Collider at CERN, Geneva, is presently the most powerful machine, which in fact proved the existence of Higgs bosons, the new particles. Historically, Rutherford's experiment on the scattering of alpha particles on the gold foil established the atomic model, which consisted of a tiny nucleus where practically the entire mass of the atom is concentrated. Before this path-breaking experiment of Rutherford, there was no viable atomic model. So, this experiment proved that the atom must have a very massive core, which is very small. So, most of the mass of the atom is concentrated in a practically very tiny space, which is called the nucleus. Existence of the constituents of hadrons, namely quarks interacting through gluons, which carry a new quantum number, which is called color, was also discovered in a scattering experiment at the SLAC National Accelerator Laboratory in the electron-proton collision. In this and in the next unit, we will briefly discuss the kinematics of elastic collision and the concept of scattering cross-section. Let us consider elastic scattering between two particles. So, we consider the scattering between two particles which have masses m1 and m2 respectively. And what do we mean by elastic scattering? By elastic scattering is meant that the internal energy of the particles, if any, remains unchanged. So, in elastic collision, the linear momentum and the kinetic energy or the mechanical energy is conserved. While considering a two-body problem, it is convenient to define the coordinates of the particle with respect to their center of mass. So, we have the two particles m1 and m2 whose position vectors are r1 and r2. The center of mass of these two particles is defined by the vector r, where the vector r is equal to m1 times the position vector r1 plus m2 times the position vector r2 divided by m1 plus m2, and then we measure the coordinate of the particles with respect to the center of mass, which are given by r1 prime and r2 prime respectively, and obviously r1 prime is r1 minus r and r2 prime is r2 minus r. Now, if we define by u1 and u2 the initial velocity of the two particles with respect to the coordinate system fixed at the origin O, and we define by u1 prime and u2 prime the velocities in the center mass system. Then from the equation which relate the coordinates with respect to the coordinate system with origin at O and the center of mass, we obtain the velocity of the center of mass v to be equal to m1 u1 plus m2 u2 divided by m1 plus m2 just simply by differentiating the position vector of the center of mass. So this is v. And likewise, the velocities of the particles 1 and 2 with respect to the center of mass are given by u1 prime is equal to u1 minus v and u2 prime is equal to u2 minus v. So where v of course is the velocity of center of mass and u1 prime, u2 prime are the velocities of m1 and m2 in the center of mass frame. In the lab frame, which is defined as the frame in which one of the particles is a target, the other particle comes and hits it. So lab frame is defined as the one in which the particle m1 strikes a stationary target m2. Thus in the lab frame, u1 is the velocity of m1 and u2 is equal to 0. v1 and v2 are the final velocities, that is velocity after the scattering of m1 and m2 respectively. So initially the particle 1 has a velocity u1, particle 2 is at rest. After scattering, the particle 1 and 2 have velocities v1 and v2 respectively. In the center of mass frame, the initial velocities of the two particles, that is u1 prime and u2 prime, and v1 prime and v2 prime are designated the final velocities of the particles. So in the center of mass frame, we designate the initial velocity of the two particles as u1 prime, u2 prime, and the final velocities as v1 prime and v2 prime. So in the center of mass frame, the motion of the center of mass is 0. So v is equal to 0, which implies that m1 u1 plus m2 u2 is equal to 0. That is, the two particles have equal and opposite momentum in the center of mass frame. So in the center of mass frame, particles come in from the opposite direction with equal and opposite momentum. The scattering between the two particles in the laboratory and in the center of mass frame would look like the following. In the lab frame, the particle m is moving with a velocity u1 and strikes a particle m2 which is at rest. So this particle is coming with a velocity u1 and strikes this stationary particle m2, and after scattering, the u1, the particle 1 moves with a velocity v1 at some angle, and the particle v2 moves, particle 2 moves with velocity v2 at some other angle. So the angle of scattering is psi with respect to the initial direction of the motion for the particle 1, and phi is the scattering angle with respect to the direction of the initial particle for the second. Phi is the scattering angle for the second particle as shown in the diagram. So this is the situation in the lab frame. The center of mass frame, the particles m1 and m2 approach each other with equal momenta. And after scattering, they go in opposite directions because the momentum has to be conserved with equal momenta again, such that the total initial and final momenta are 0. So the picture you have for scattering in the center of mass frame is that two particles are moving towards each other with equal and opposite momenta. Before scattering and after scattering, they separate out in opposite directions, again with equal and opposite momenta. The conservation of linear momentum and kinetic energy implies that the center of mass velocities of m1 and m2 before and after the collision are equal. That is, u1 prime is a v1 prime, u2 prime is equal to v2 prime. The final center of mass velocities are v1 prime is equal to u1 prime is equal to u1 minus v, is equal to, where v is the velocity of the center of mass. The magnitudes here we have written. So v1 prime is equal to u1 prime is equal to u1 minus v, which is equal to u1 minus, and velocity of the center of mass is m1 u1 divided by m1 plus m2. Therefore, v1 prime is m2 u1 divided by m1 plus m2. Likewise, v2 prime is equal to m1 u1 divided by m1 plus m2. So if you look at the scattering diagram, which is, so v here in the diagram we have shown v is the velocity of the center of mass, then this here theta is the scattering angle with respect to the initial velocity, and you have this the velocity v, that is the velocity of center of mass, and the initial velocity of the particle 1 and the final velocity of particle 2 form a triangle. The angle between the velocity v and v1 prime is theta, and from this triangle we can see that v1 prime sine theta is equal to v1 sine c. Now this, and then v1 prime cosine theta plus v is equal to v1 cosine psi, and from here have tangent psi is equal to v1 prime sine theta divided by v1 prime cosine theta plus v, which can be written as sine theta divided by cosine theta plus v by v1, which is equal to sine theta divided by cosine theta, and v by v1 is m1 by m2. Now we can consider special cases. Let's consider the case where the target particle is very heavy compared to the particle which hits it. So m2 is much greater than m1. When m2 is much greater than m1, in the expression of tangent psi, m1 by m2 goes to 0, and therefore tangent psi is sine theta by cos theta is equal to tangent theta. So we have the result that the scattering angle in the lab and the center of mass frames are approximately equal for the case when the target particle is very heavy compared to the projectile. In this case, the particle m1 essentially scatters from a fixed scattering center. In the case when the two particles have equal mass, m1 is equal to m2, tangent psi becomes equal to sine theta divided by 1 plus cosine theta, which is tangent theta by 2. And the scattering angle in the lab frame is equal to half the scattering angle in the center of mass frame. Further, since the maximum value of the scattering angle theta in the center of mass frame is 180 degrees, the scattering angle in the lab frame for the case when the two particles have equal mass cannot be greater than 90 degrees. That is to say, there is no back scattering. So if the two particles of equal mass collide with each other in the lab frame, there cannot be any back scattering. Let us now look at the scattering of the second particle, that is of the recoil particle, M2. M2 scatters by an angle phi, which satisfies V2 sin phi is equal to V2 prime sin theta, and V2 cos phi is equal to V minus V2 prime cosine theta. We have then tangent phi is equal to sin theta divided by V2 minus cosine theta, which can be expressed as sin theta divided by 1 minus cosine theta, because V is a V2 prime. We thus get tangent phi is equal to cotangent theta by 2, which is tangent pi by 2 minus theta by 2. Therefore, phi is equal to pi by 2 minus theta by 2. And from the equation 1210, for m1 is equal to m2, psi plus phi is pi by 2 for m1 is equal to m2. The energy expressions in the elastic scattering and the relationship between expressions in the lab and the center of mass frame can be easily obtained. The initial energy of the particles in the lab frame is E0 is equal to half m1 u1 square. The particle 2 being at rest in the lab frame, its energy, the mechanical energy, is equal to 0. Whereas in the center of mass frame, the energy E0 prime is equal to half m1 u1 prime square plus half m2 u2 prime square, which is m2 divided by m1 plus m2 E0. The final center of mass energies are therefore E1 prime is equal to m2 divided by m1 plus m2 whole square into E0, and E2 prime is 1 minus m1 m2 divided by m1 plus m2 whole square times E0. The energy of m1 in the lab frame is E0 is equal to 1 minus 2 m1 m2 divided by m1 plus m2 whole square 1 minus cosine theta in terms of center of mass scattering angle, then substituting for theta, we get the expression E1 by E naught is M1 square divided by M1 plus M2 whole square multiplied with this expression, which is cosine psi plus minus under root of M2 square by M1 square minus sin square psi whole square. So in terms of the scattering angle psi, the lab energy of the recoil particle M2 is given by E2 by E naught is equal to 1 minus E1 by E naught is 4 M1 M2 divided by M1 plus M2 whole square cosine square phi. Now let us see how the scattering cross-section is defined and what a scattering cross-section is. In a scattering experiment, when the particle interactions are known in terms of the force field, it is possible to predict the scattering outcome in terms of the final energies and the scattering angles of the particles. Conversely, if you do an experiment and you have the data about the final energies and the scattering angles of the particles, then one can discern from this the nature of the force field. So, we will now investigate the scattering process in the presence of a force field. Let us consider the collision in the laboratory system in the presence of a repulsive force between the two particles M1 and M2. So, this figure depicts the scattering. The particle M1 is coming from the left with an impact parameter B, which is the minimum distance between the particle from which it is scattering, and as it reaches the particle, because the repulsive force, it bends, its path bends, and it scatters by an angle psi as shown here in the diagram. So, the particle M1 approaches the particle M2 such that if there was no force between them, the particle M1 will pass through in a straight line with an impact parameter B. So, it's a particle M2 here, a particle M1 coming with impact parameter B2. If there is no force, it just goes past it. And if there is no force but there is elastic collision, then because elastic scattering takes place. But the impact parameter has been defined as the distance of closest approach between the two particles. So, this impact parameter being defined in this way is the distance of closest approach. If the particle M1 is moving with an initial velocity u1, then the angular momentum of M1 about M2 is clearly equal to M1 times u1 times b, and the initial velocity u1 can be written as under root twice E1 by M1. Thus, if the force field is known, that is, if the interaction between the particles is specified, then for a given initial energy and impact parameter, because how is the experiment done? You send a beam of particles with a fixed initial energy at a certain with a certain impact parameter, and then you measure the scattering angle and the final energies. Or if you know the force field, then you can predict the scattering angle and the final energies. In actual practice, we have a beam of particles of mass m1 and fixed energy E naught moving towards a collection of particles of mass m2 each, and in the laboratory frame which are at rest. We define the flux of the incident particles as the number of particles which passing through a unit area normal to the beam direction per unit time. So, the beam is coming like this, take a unit area perpendicular to the beam. So, number of particles which are passing through this unit area is defined as the flux. If the force between the particles falls off sufficiently fast with distance, the initial and final paths will be straight with an angle theta between them. if the force between the particles falls off sufficiently fast, with this change, their initial and final paths will be straight with an angle theta between them. If dn is the number of particles is scattered into an element of solid angle d omega per unit time in the center of mass frame, we define differential cross-section as sigma theta d omega. So this is the definition of a differential cross-section. Sigma theta d omega is equal to dn by f, where dn is the number of particles scattered into an element of solid angle d omega per unit time, and f is the flux. That is, sigma theta is equal to d sigma by d omega is then equal to 1 upon f dn by d omega. So sigma theta here, you can see, has the dimensions of area. Why does it have the dimension of area? N is the number of particles scattered. F is the flux per unit area. So number of particles per unit area, d omega is dimensionless, so sigma has the dimensions of area. For central forces, the scattering has azimuthal symmetry. There is no dependent on the azimuthal angle phi, and d omega then can be written as 2 pi sine theta d theta. But for central force, there is no dependence on the azimuthal angle. Let us see what happens in the center of mass frame. In the figure which you will see, notice that the number of particles scattered between the angle theta and d theta is equal to the number of particles which have impact parameter lying between b and b plus db. So how many particles have their impact parameter lying between b and b plus db? That is equal to the flux times this area, which is 2 pi b db. So F into 2 pi b dB is equal to dn, which is equal to minus F sigma theta 2 pi sine theta d theta. The negative sign indicates that the scattering angle decreases with increasing impact parameter. So what we have said earlier can be seen from this figure. So all those particles which have their impact parameter lying between b plus db, which is equal to the area of this annular region, which is 2 pi b db, and the number of particles in this is 2 pi b dB into flux. All these particles scatter by an angle of theta plus a d theta. Therefore, sigma theta from this expression can be easily seen to be b upon sine theta, the magnitude of dB by sine theta. Now, b is the impact parameter which is related to the angular momentum, as L is equal to under root 2 m1 E naught b, where m1 is the mass of the particle which is scattered. Now we can write down the change in the scattering angle moving in the central field from the expressions which we have obtained earlier while considering the change in angle in the motion of a particle in the central field. So this change of angle, if we represent by delta omega from when the particle moves from a position r minimum to r max, then delta omega is equal to integral from r min to r max of L by r square divided by under root of 2 mu E minus U minus L square divided by 2 mu r square half. The motion of a particle in the central field is symmetric about the point of closest approach, as can be seen in the diagram below. So the motion of the particle is symmetric. The point of closest approach is given by this, as can be seen in the diagram. The relationship between theta and this angle omega, which is the change in the scattering angle, is theta is equal to pi minus 2 omega. So in the case of scattering, the initial energy is positive and the orbit is open. So the particle of scattering can go over to infinity. Therefore, omega is given by an integral from r minimum to infinity of b by r square dr divided by under root of 1 minus b square by r square minus u by E naught. R minimum is the turning point, and is given by the root of 1 minus b square by r square minus u by E naught, and is the closest distance of approach of the particle from the center of force. In the case when M2 is much greater than M1, the cross-section thus obtained is very near equal to the cross-section obtained in the center of mass frame. The total scattering cross-section sigma t is obtained by integrating the differential cross-section sigma theta or sigma psi working in the left frame or the center of mass frame over all possible scattering angles theta and psi in the center of mass and left frames respectively. It is equal to the effective area of the target particle, and the total cross-section sigma t is equal to 2 pi times sigma theta sin theta d theta in the left frame, and sigma t is equal to 2 pi times the integral sigma psi sin psi d psi in the center mass frame, where theta runs from 0 to pi in the center mass frame and psi runs from 0 to pi for M1 much less than M2 in the left frame. So, students, in this module, you have learned about the elastic scattering, and you saw that in elastic scattering, both the linear momenta and mechanical energy is conserved. You learned that in the center of mass frame, the sum of the momenta of the colliding particles is 0. So, both before and after the scattering, if the colliding particles have equal mass, the scattering angle in the left frame is 1/2 of the scattering angle in the center of mass frame, and the differential cross section is defined as the number of particles is scattered into an element of solid angle d omega per unit flux of the initial particles. In the scattering experiment, once the particle interactions are specified in terms of the forces, the scattering outcome in terms of the scattering angle and final energies are predictable,